Hi, wishing you all. I'm Dr. J. Associate Professor of Physics, Institute of Aeronautical Engineering. Today I wish to tell about the topic of helium neon laser. So in this helium neon laser topic, we are going to cover the introduction about the helium neon laser and the construction of helium neon laser and working advantages, and also we are going to see the disadvantages in this helium neon laser, and then finally we are going to see the applications. So these are the topics we are going to cover in this session. So let us see the introduction. Helium neon laser. Helium neon laser was fabricated by Ali Javon W. Bennett and then D. Harriet in 1961. So this helium neon laser was the first gaseous state laser which was successful. Helium neon laser was the first gaseous state laser and it is successful to use light radiation. So we can obtain light radiation with high coherence, high directionality and higher monochromaticity. But the output power in this helium neon laser is up to few milliwatts. So here from this helium neon laser, we can obtain light radiation with higher coherence, higher directionality and higher monochromaticity. But the output power of this helium neon laser is generally up to few milliwatts. So for increase, why we are using this helium neon laser is to increase the efficiency and getting the continuous emission of laser. So for increased efficiency and continuous emission of laser, we prefer helium neon laser. Coming to the construction, helium neon laser is a continuous 4-level gas laser. It is a continuous 4-level gas laser, where in the previous session we have been talked about the ruby laser. So that ruby laser is the first solid state laser. So there we have seen some drawbacks. So in the drawbacks, one of the drawback is it is a pulsed laser. But here in helium neon laser, it is a continuous laser. Where in the case of ruby laser, it is a 3-level laser, but here it is 4-level gas laser. So helium neon laser is a continuous 4-level gas laser. It consists of a long, narrow cylindrical tube made up of fused quartz. It has long, narrow cylindrical tube. So that cylindrical tube diameter will be vary up to 2 to 8 millimeters, and the length of the cylindrical tube varies from 10 to 100 centimeters. 10 to 100 centimeters. So this cylindrical tube, this long narrow cylindrical tube is filled with the helium and neon gases, both the gases we are taking. So helium and neon gas mixture have been taken in this narrow cylindrical tube, and the gas mixture have the ratio of mixing, so 10:1. So the tube is filled with helium and neon gases in the ratio of 10:1. The partial pressure of helium gas. The partial pressure of helium gas is 1 millimeter of mercury, and neon gas is 0.1 millimeter of mercury. So that overall the pressure of the mixture of gases, so mixture of gases here helium plus neon, both the gas mixture we are taking. So the pressure of the gas mixture inside the tube is nearly 1 millimeter of mercury. The actual lasing atoms. So the actual lasing atoms or neon atoms. Helium is used for selective pumping of neon atoms to upper energy levels. So actual lasing action is done by the neon atoms, but here the helium atoms are used for pumping. So helium is used for selective pumping of neon atoms to excited energy levels. So the gas mixture will serve as active medium. This gas mixture will serve as active medium. Two electrodes are fixed near the ends of the tube to pass electric discharge through the gas to excite the helium atoms, and in turn neon atoms will act as a source of energy. The discharge tube is enclosed between fully and partially reflective mirrors, which serves as optical cavity or optical resonator. And here, these two mirrors have been taken. One of the mirror is fully silvered so that nearly 100% of reflection takes place, and the other mirror is partially silvered so that 1% of incident light will be transmitted. So here, two electrodes are fixed near the end of the tube, that is long narrow tube. The two electrodes are fixed near the ends of the long narrow tube to pass electric discharge. So this electric discharge pass through the gas to excite the helium atoms so that neon atoms will act as a source energy. So the discharge tube is enclosed between the fully and partially reflective mirrors, which serves as an optical cavity or optical resonator. And here the fully and partially reflective mirrors, one is fully silvered, that is 100% reflection takes place here, and the other is partially silvered so that 1% only the light incident will be transmitted. This is the experimental setup of helium and neon laser. Um, Here the gas mixture have been taken here, helium plus neon. So helium has been taken 10 or 10 is to 1 ratio. 10 is to 1 ratio. And the end faces, the near the end of the tube, this is the tube. At the near the end of the tube, two electrodes are fixed. Two electrodes are fixed to through this uh, electrodes. Through this electrodes, we are passing electric discharge. So when this electric discharge passes through the gas, what happens? It excites the helium atoms, and in turn neon atoms acts as a source energy. And the end faces of this tube, the end faces of this tube is partially silvered. One end of the face is a partially silvered mirror, and the other face is fully silvered mirror. So it has the discharge tube end faces are partially silvered and other face is fully silvered mirror. The laser output can be obtained by the partially silvered end. Coming to the working of this helium neon laser, when discharge is passed through the gaseous mixture, that is a helium plus neon mixture, electrons are accelerated. When discharge is passed through the gaseous mixture from the discharge electrodes. Electrons are accelerated. So these accelerated electrons collide with the helium atoms, which are more in number, raising them to higher energy levels F2 and F3. Helium atoms in the excited levels. Helium atoms in the excited levels spend sufficiently large amount of time before getting de-excited. Some of the excited states of neon can correspond approximately same energy of excited energy levels F2 and F3. The helium atoms in level F2 and F3 collide with neon atoms by inelastic collision. Energy transferring takes place here. So, helium atoms, after transferring their energies to neon atoms by inelastic collisions, they may get de-excited to F. So the energy is transformed from the helium atoms in level F2 and F3 when it is colliding with neon atoms. So because of inelastic collision, the energy will be transferred to neon atoms. So this helium atoms get de-excited and they transits to F1. They comes to lower energy level. Now, the neon atoms are in the excited state. So, neon atoms are excited to E4 and E6. E4 and E6, which have nearly the same energy as the levels F2 and F3 of helium. So, this results in the excitation of neon atoms to the levels E4 and E6, which have the same energy as the levels F2 and F3 of helium, and the excitation of helium atoms to the ground level F1 takes place. Because of long lifetime of the atoms in the F2 and F3, this process of energy transfer has a high probability because of long lifetime of the atoms in levels F2 and F3. This process of energy transfer has a high probability. Thus, the discharge through the gas mixture continuously populates the neon atoms in the excited energy levels E4 and E6. So, thus, the discharge through the gas mixture continuously populates the neon atoms in the excited energy levels E4 and E6. So, this helps to create a state of population inversion between the energy levels E4 and E6 to the lower energy levels E3 and E5. So, energy levels E4 and E6 to the lower energy levels E3 and E5. So, here F2 means the energy levels of the excited energy levels of the helium. So thus, a state of population inversion is achieved and any spontaneous emitted photon, any spontaneous emitted photon can trigger laser action in any of the three transition of the energy levels. The neon atoms then drop down from the lower laser levels to the levels E2 through spontaneous emission and are brought back to the ground state through collisions with the walls. So, the neon atoms then drop down from the lower energy levels to the levels E2 through spontaneous emission and are brought back to the ground state through collisions with the walls. The transitions from A6 to E5, E4 to E3, and A6 to E3 result in emission of radiation having wavelengths 3.39 micrometer, 1.15 micrometer, and 6,328 angstroms respectively. The radiations of wavelengths 3.39 micrometer, 1.15 micrometer are invisible, whereas the radiation with 6,328 angstrom is red in color. So the transitions E3 to E2 is spontaneous. From E2, the neon atoms get de-excited by collision with the walls of the discharge tube. So the excitation and de-excitation of helium and neon atoms is continuous process, and thus it gives continuous emission of laser radiation. Let us see the energy level diagram, how the helium atoms gets excited and how it collide with the neon atoms. When it collide with the neon atoms, how it grabs the energy of the helium atoms, then how it can be uh, transits to lower energy levels and to the ground energy level by de-exciting. So this is the relevant energy levels of helium and neon laser. So here we have taken the helium atoms beside neon atoms. So when the electric discharge pass through the discharge tube, electric discharge pass through the gas mixture. So electrons accelerated. So these accelerated electrons collides with the helium atoms. So when the accelerated electrons collides with the helium atoms, which are at the lower energy level F1, they get excited. They get excited. So there is excitation due to collision with electrons. So due to excitation due to electrons, helium atoms excited to F2 and F3 energy levels. F2 and F3 energy levels. Now, this excited helium atoms collides with the neon atoms, collides with neon atoms, so which are nearly having the same energy levels as of helium excited energy levels F2 and F3. So energy exchange takes place through atomic collisions between helium and neon atoms. So here inelastic collisions takes place between the helium atoms and neon atoms. So the excited atoms from the energy levels F2 and F3 collides inelastically with neon atoms which are at E6 and E4. So because of inelastic collisions, these neon atoms gains energy from the helium atoms, and after transferring energy to the neon atoms, these helium atoms get de-excited. So from F2 and F3, they comes to de-excited to F1 energy level. Now, the neon atoms transits from, that is after the lifetime 10 power minus 8 seconds. After the lifetime, the neon atoms from the excited state E4 and E6 transits to lower energy levels E6 to E5, E4 to E3, E6 to E3. So here the E6 to E5 have the wavelength 3.39 micrometer. E4 to E3, the wavelength is 1.15 micrometer. E6 to E3, 6,328 angstroms. So these two transitions are invisible region. But here E6 to E3 having wavelength 6,328 angstroms, so they are red in color. Okay. So because of long lifetime at the energy levels F2 and F3, it has more probability in the higher energy level. So the discharge tube which have the gas mixture continuously populates the neon atoms in the excited energy levels E4 and E6. So it achieves a state of population between E4 and E6 to the lower energy level E3 and E5. So that a state of population inversion is achieved at any spontaneous emitted photon can trigger laser action in any of the three transitions. That is, the three transition means E6 to E5, E6 to E3, E4 to E3. So, that is transition E6 to E5, E6 to E3, and then E4 to E3. So, any of the three transition triggers the spontaneous emission. So, a state of population is achieved at any spontaneous emitted photon can trigger laser action of in this any of the three transitions. So, any spontaneous transition, any spontaneous emission may trigger. So, in these three transitions, so that it takes place. So E3 to E2, there is a spontaneous emission. This transition of E3 to E2 is spontaneous emission. After this spontaneous emission, so they may get de-excited because of colliding with the discharge tube. So they de-excited by the walls and they fall back to the lower energy state. So like this, the laser transition, the lasing action, lasing action takes place in this helium neon laser. So because of any of the spontaneous emission may trigger to get the stimulated emissions, so that continuously that stimulated emission occurs. So when the photons are multiplied, so they may reflected back and forth between the reflective mirrors. So at a high intensity, when the photons are high intense, then they would come out from the partially reflective mirror. So we get the laser beam from the partially reflective mirror. So here, what are the advantages of this helium neon laser? So it is a gas laser, as early we have said. Gas lasers emit more monochromatic and directional laser radiations when compared to the solid state lasers. Helium neon laser emits continuous laser radiation due to setting of windows at a Brewster's angle. So the output laser is linearly polarized. And so that is Brewster angle. So means that the discharge tube. So like this shape Brewster angle, the end windows are set up so that the output, because of setting of the windows at the ends in the Brewster angle, the output laser is linearly polarized. And the helium neon laser have a high stability, it has a low cost, and it operates without damage at high temperatures. These are the advantages of the helium neon laser. Coming to the disadvantages, helium neon laser has a low efficiency, but it has increased efficiency when compared to the ruby laser. As in the case of ruby laser, it is a pulsed laser, but here it is a continuous laser, and we are getting here increased efficiency. It has low gain. Helium neon laser has low gain. And seeing about the applications, helium neon lasers are very useful in making holograms. They are used in interferometric experiments. Coming to the medical field, in medicine, this acts as an aiming laser. This acts as an aiming laser, means that which is generally used to identify the spot where the laser surgery has to be performed. So, in medicinal point of view, this acts as a aiming, so that the surgeon can easily identify the spot of the surgery point to do the surgery. So, in medicine, this acts as an aiming laser, which is normally used to identify the spot where the laser surgery has to be performed. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.